Hey everyone, this is Derek, and this is going to be the first of two videos about optimizing functions of two variables. And so the first video is going to be about finding critical points, and the second video will be about the actual optimization. And when we optimize, remember that's where we're finding like local mins and maxes. And in this case, when we're looking at functions of the form z equals f of x, y. So remember this, we're putting in an x and a y, and then we're getting out that z coordinate. We get these different surfaces in space, and they can look like lots of different things, but here's just an example of three of them. So we could have something kind of parabolic down, and then we'd have a minimum value there. We could have something sort of parabolic up, and so then we'd have a maximum value right here. And then there's these saddle points, and those can also, I'll talk about in the second video how to find those as well. So these first two are just kind of formal definitions of maxes and mins. A critical point for the function f of x is a point where these two things are true. So remember, the critical points are going to be where we would find these local maxes and mins. And so if you remember back when we did these with just x and y, we'd take the derivative, set it to 0, and that's how we found our critical values or critical points. We're going to do the same thing here, but now we're just going to do the partial with respect to x has to be 0, and the partial with respect to y has to be 0, or undefined. Okay, so we're going to find the critical points of this function, and remember these are the two conditions that we have to meet. And again, this or undefined. I don't think we have any in this section that are undefined, so it's pretty much going to be where they equal 0. So the first thing I'd want to do is take the partial with respect to x, set it to 0, take the partial with respect to y, set it to 0, and then solve whatever that does. Maybe I just get values out, then those are my values, and then maybe I get something a little bit more complicated that I'll have to solve for x and y. So for this one, let's take our partial with respect to x. So this is going to be a 2 down front, x over 2, and then again, a 2 down front. Oh, shoot, I'm doing x. See what I just tried to do? It's a y. So remember, when it's a y, that's a constant, and don't do what I just started to do right there. And then right there, we'll have 1 times negative 5. It's just messy. So negative 5. So this 7y will drop out because that's just acting like a constant. This one doesn't have an x, so this would be like 1 times whatever that constant would be, so that'd be minus 3y. And then just writing that slightly less terrible, that would be x minus 5 minus 3y. So there's that. And then we'll do the same thing. We'll do the take the partial derivative with respect to y. So that time this will drop out, and then fy, so it'll be 2y over 2. The 5x term drops out. 7y would be just a 7. This one does have a y, so that'll be a minus 3x. Cancel the 2's. So now that I have that, what I basically have here is two linear equations. And so to solve two linear equations, we can either do substitution or elimination. I think I'm going to set these up to do an elimination problem. So for here, what I'm basically doing is I'm setting this to 0, and then I'm going to add the 5 over. So that's going to give me x minus 3y equals 5. And that feels a little bit more like in a form that we can work with. And then same thing over here. I think I will, what did I do? Yeah, I'm just going to add the 3x and the y over. So we'll go plus, have 3x here, and then minus on the y. And then that will equal 7. And now that I have that, I'm going to, I think I'll multiply this top one by negative 3. And so this will be negative 3x, and then plus 9y. Negative 3 times 5 will be negative 15. Now let's bring this one down. And x's drop out, and we got 8y equals negative 8. So it looks like y equals negative 1. And now that I know that, I can come back to either of these equations and solve for the y value. So I'll just throw the, or solve for the x value, excuse me. So I'll go ahead and throw the y in right here. So it'll be x minus 3 times negative 1 equals 5. So it would be x plus 3 equals 5. So then subtracting that over, I would get x equals 2. So it looks like my solution is 2 and negative 1. Okay, so same idea here. So first we'll find the partial with respect to x. So that's going to go, bring the 2 down. 2 times 5 would be 10, but then canceling the 2's, and we're right back to that 5. That term only involves y, so it will drop out. Again, this term only involves y, so it will drop out. And then that doesn't have an x, so that will drop out. So that's what we got for f of x, or sorry, partial with respect to x. And then partial with respect to y, x term drops out. This one's going to be 4y cubed over 2, and then minus 8. And then reducing, I will have 2y cubed. Oh, that was y squared. That should have an 8y, sorry, minus 8y. So now I have to solve these. If I set these to 0, 0 equals 5x, okay, dividing over, x is going to equal 0. This one, so if I do 2y cubed minus 8y equals 0. So here I'll have to do a little bit of factoring to get this to work. So I'm going to take out a 2y. That will leave me a y squared minus 4. And then this factors one more round. So we'll do 2y, y plus 2, and y minus 2 equals 0. So now we have y equals 0, and then this would be y equals negative 2, and y equals 2. So that means my critical points are going to the x's all have to be zeros, and then these will be the y coordinates. So we'd have 0, 0, 0, negative 2, and 0, 2. Okay, so for this one, we're finding the critical points of an exponential. So just remember, when we have an exponential function, we take the derivative, we end up with just the derivative of the exponent, and then times e to that exponent. So let's see what we can get here. With this, our u in this case would be the 5xy, and our u prime is going to be, so that has a 1, so that our u prime will be 5y. And then taking the derivative, I will have u prime, so 5y, times the original function, and with the u filled back in. So that would be my my derivative with respect to x. So then I will do the same thing for y. And if we do that, we're going to get the same thing, except it will be an x instead of a y. And that's because when we, right here, when we make this 5xy our u, and we take our derivative, this time it's with respect to y, and so the y would drop out and I'd have a 5x, and then the rest of it goes just like this one. And then once we're there, now we just have to solve each of these. And you can see they're basically the same form, so if I'd solve one, I could solve the other. So I'll just grab that top one and say 0 equals 5y times e to the 5xy. So this is 0 equals something times something. So if I have, 0 equals a times b, then either a is 0 or b is 0, because that's how it would come out to 0. So here if I go 0 equals 5y, then I divide over the 5, I have y equals 0. This one, if I have 0 equals this multivariable thing, that can't happen, because remember, exponentials, they approach the axis, but they don't actually cross it. And so then we do the same thing for the second function, and you can see it's just going to end up at 0 equals 5x, and so it doesn't look like a 5x. 0 equals 5x, and so then x is also 0. So our point would be at 0, 0.